We turn now to the urgent new warning about the potential dangers of artificial intelligence. Top experts and executives in the field say it poses, quote, the risk of extinction, comparing it to pandemics and nuclear war.
Have you ever wondered what might happen if we combine AI and quantum computers? Would this combination destroy our planet or enhance our understanding of the universe? As technology progresses, we are eagerly awaiting the arrival of quantum computers. Scientists are working tirelessly to develop these advanced machines. However, there has been a recent development where the U.S. government has pressured Google and NASA to shut down their quantum computer development efforts after something terrifying happened.
And also where Google met the challenge. They beat a standard supercomputer at a certain select question. So in other words, we have already achieved quantum supremacy. That is, quantum computers on select problems can exceed the capability of any digital computer.
This news is accompanied by a disturbing announcement from famous physicist Michio Kaku about the potential dangers posed by the combination of quantum computers and AI.
That's the reason why they're so dangerous, because they don't know. These chatbots are machines. They don't know what is correct, what is incorrect. It's all the same to them. That's the danger.
Right.
Now,
That's what
remember
I'm talking
that
about.
if this is not done legally, if there are no laws passed in this direction, and it's like the Wild West, then, of course, the politicians get involved, and it becomes a real mess.
Let's dive in and explore the fascinating world of quantum computers and how they will change everything. Quantum computers are a revolutionary type of computer that operates based on the principles of quantum mechanics. Unlike classical computers that use bits to store and process information, quantum computers use quantum bits or qubits. In classical computers, bits are the fundamental units of information and can be in one of two states, 0 or 1. They represent the foundation of digital computing and are used to perform calculations and store data. However, qubits in quantum computers possess a property called superposition, which allows them to exist in multiple states simultaneously. This means that a qubit can be both 0 and 1 at the same time. The ability of qubits to exist in superposition is what makes quantum computers so powerful. It allows them to perform computations in parallel, simultaneously exploring different states and possibilities. This parallelism can potentially enable quantum computers to solve certain problems much faster than classical computers. The history of quantum computers can be traced back to the early 1980s, a time when physicist Richard Feynman first proposed the revolutionary concept of quantum computation. Feynman envisioned the creation of a novel type of computer that could utilize the principles of quantum mechanics to solve complex problems that were beyond the capabilities of classical machines. However, it wasn't until the 1990s that significant breakthroughs started to emerge in this field of study. In 1994, a mathematician named Peter Shor, working at Bell Labs, unveiled a groundbreaking algorithm for quantum computers. This algorithm had the remarkable ability to efficiently factor large numbers. The significance of this discovery cannot be overstated, as factoring large numbers forms the foundation of many encryption methods used to secure sensitive information in today's digital world. Shor's algorithm opened up new possibilities and ignited both excitement and concerns within the scientific community, as it demonstrated the immense potential of quantum computers in breaking conventional cryptographic systems. Throughout the 1990s and early 2000s, researchers delved into various approaches to constructing practical quantum computers. One of the most promising technologies involved manipulating individual atoms or ions to serve as qubits, the fundamental units of information in quantum computing. In 2001, a team of scientists at IBM achieved a significant milestone by successfully demonstrating the concept of quantum computing using nuclear magnetic resonance to control qubits. This achievement showcased the feasibility of quantum computation and served as a catalyst for further advancements in the field. As the field progressed, researchers made remarkable strides in developing more robust qubit systems. They explored different types of qubits, such as superconducting circuits and trapped ions, each possessing distinct advantages and challenges. These advancements paved the way for the construction of increasingly complex quantum computers with a growing number of qubits, enabling more sophisticated calculations and simulations. In 2013, Google and NASA joined together to create a quantum computer. The plan was to set up a special quantum computer known as the D-Wave 2 at NASA's Ames Research Center. But just when everything was getting started, there was a problem. The government was about to shut down, which meant that NASA might have to close its doors. This was a big issue because it could stop the quantum computer project from moving forward. The timing couldn't have been worse. The D-Wave 2 had already been turned on and was ready to be used, but now its future was uncertain. It would have been expensive and time-consuming to turn it off and then turn it back on when things went back to normal. So, even though the computer was on, it couldn't be used to its full potential. It was in a kind of in-between state, just using up electricity without doing anything useful. For Google, this situation was confusing. They had invested in a special lab called the Ames Quantum Artificial Intelligence Lab, which gave them access to the quantum computer. But with the lab shut down, they didn't know what they could do with it. A spokesperson from Google said that the computer was still working, but they couldn't say much about what they were doing with it or their future plans until NASA was fully operational again. The government shutdown had a big impact on the project. NASA's testing and exploration of this new and exciting technology had to stop. It was a frustrating loss of time and missed opportunities. The people working on the project were disappointed that they couldn't make progress and move forward. In 2019, Google made headlines again with its announcement of achieving quantum supremacy. Utilizing a superconducting quantum processor called Sycamore, Google's team successfully solved a highly complex mathematical problem that would have taken classical computers thousands of years to compute. This achievement demonstrated the superior computational power of quantum computers in specific tasks and sparked a renewed wave of enthusiasm and investment in the field. Inspired by Google's breakthrough, other major tech players like IBM and Microsoft intensified their efforts to develop quantum computers, fueling a race to create more powerful and reliable quantum systems. However, researchers encountered numerous challenges in their pursuit of scalability. Quantum systems are extremely delicate and vulnerable to errors caused by environmental disturbances, a phenomenon known as DeCoherence. To overcome this obstacle, scientists focused their efforts on developing error-correcting codes and fault-tolerant techniques that could protect fragile quantum information from external interference. The year 2020 marked another significant milestone in the history of quantum computers. IBM unveiled the IBM Q System 1, the first fully integrated quantum computer designed for commercial use. This achievement represented a major step towards making quantum computers more accessible and practical for a wider range of applications. With the exponential growth of quantum computing research, the field began to attract substantial attention and investment from governments and industries worldwide. Recognizing the transformative potential of quantum computers, governments allocated significant funding to support quantum research initiatives, leading to the establishment of quantum research centers and laboratories that fostered collaborations between academia, industry, and government agencies. Modern scientists believe that extraterrestrial intelligent life exists, but they might be using black holes as quantum computers, and that's why we can't find them. The Fermi Paradox has puzzled astronomers and cosmologists for years. With the high probability of life existing elsewhere in the universe, why haven't we found widespread evidence of it? The Hart-Tipler conjecture attempts to address this paradox, suggesting that if advanced extraterrestrial civilizations had emerged in our galaxy, we would see signs of their activity everywhere.
I think outside the Earth, there could be a superhighway, a laser highway, of laser porting with billions of souls of aliens zapping their way across the galaxy. Now let me ask you a question. Are we smart enough to determine whether such a thing exists or not? No. This could exist right outside the orbit of the planet Earth, and we're too stupid in our technology to even prove it or disprove it.
Is it the case that any sufficiently advanced civilization destroys itself? Is that sort of a commonplace quality? I mean, that's the other potential answer to the Fermi paradox. Why aren't they here? Because by the time they got to the technological development where they could travel here, they blew themselves up. They destroyed themselves. And that's an unfortunate but not a hard to imagine possibility based on things that have happened here on planet Earth.
However, a recent study by a team of German and Georgian physicists proposes an intriguing explanation. These civilizations could be utilizing black holes as quantum computers. Since the first SETI, Search for Extraterrestrial Intelligence, survey. In 1960, scientists have primarily focused on searching for radio signals from distant star systems. However, this narrow approach might be limiting our chances of success in finding evidence of extraterrestrial life. Recent suggestions include expanding the search to other techno-signatures such as directed energy, neutrino emissions, quantum communications, and gravitational waves. The study conducted by Gia Dvali and Zaza Osmanov takes a different approach, exploring the possibility of large-scale quantum computing as a potential techno-signature. Dvali and Osmanov proposed that black holes could serve as the ultimate source of computation for advanced extraterrestrial civilizations. Quantum computing offers significant advantages, such as exponentially faster information processing and resistance to decryption. Given the rapid progress in quantum computing technology, it is plausible to assume that advanced civilizations would adopt this technology on a larger scale. The researchers argue that black holes, based on the laws of quantum physics and gravity, are the most efficient storers of quantum information. In other words, black holes provide the ideal conditions for quantum computing. These hypothetical black holes would likely be artificially created and micro-sized to maximize computational efficiency. As a result, they would emit higher intensity radiation, including a phenomenon known as Hawking radiation. Hawking radiation is a theoretical concept proposed by the late physicist Stephen Hawking. Could serve as techno-signatures, indicating the presence of advanced extraterrestrial civilizations. The emitted radiation would consist of various subatomic particles, including high-energy neutrinos. Neutrinos are elementary particles that have extraordinary penetrating abilities, making them ideal carriers of information and difficult to screen or obstruct. According to the researchers, high-energy neutrinos could originate from both the Hawking radiation of micro-black holes and the particle collision factories used to manufacture them. The Ice Cube Observatory, a detector buried deep in the ice of Antarctica, is mentioned as a potential instrument capable of detecting such techno-signatures. This theory offers a potential resolution to Fermi's paradox and the silence observed in the cosmos. If advanced extraterrestrial civilizations have already transcended radio communications and digital computing, it is logical to assume they would have transitioned to using black holes as quantum computers. This shift could explain why we have not detected any techno-signatures from such civilizations. Additionally, the exponential progress of computing technology suggests that these civilizations might have a limited window during which they use radio wavelengths for communication. This aligns with the L parameter in the Drake equation, which represents the length of time civilizations actively release detectable signals into space. Michio Kaku is a renowned theoretical physicist, futurist, and popular science communicator. He is known for his work on string theory and his ability to simplify complex scientific concepts for the general public. Michio Kaku frequently discusses cutting-edge technologies and their implications for the future. His recent book, Quantum Supremacy, delves into the exciting realm of quantum computing. Recently, Dr. Michio Kaku discussed the impact of AI chatbots and quantum computing in a podcast episode. He explained that AI chatbots, while capable of generating thoughts and ideas, lack the ability to discern what is accurate or incorrect. Quantum computers, on the other hand, have the potential to act as fact-checkers for AI systems, ensuring more accurate results. However, Dr. Kaku expressed concern about the control of fact-checking capabilities, as governments could manipulate information and suppress dissenting voices. Quantum computing could either greatly improve human society or be used as a weapon of deception and control, depending on how it is used. The rise of AI has been rapid, with AI image generators and chatbots making significant progress. However, there are hidden dangers associated with AI technology. Deepfakes, for example, can be used to spread political misinformation and create false accusations against individuals. The ability to generate realistic images, videos, and audio recordings raises concerns about the authenticity of evidence and the confusion it can create. AI technology also poses risks in international conflicts, as deepfakes can be used to falsify orders and sow confusion among the public and armed forces. In law enforcement, AI tools can contribute to over-policing and biased decision-making, leading to higher rates of pretrial detention and harsher sentencing, particularly for marginalized communities. The inherent biases in AI models, influenced by existing societal biases, further exacerbate inequality. Moreover, AI language models can produce hallucinations, providing false information that could potentially lead to harm. The stock market is also vulnerable to AI trading bots, which could cause significant market shocks. AI's potential to revolutionize internet search raises concerns about the collapse of the digital advertising market and the effectiveness of search engines. Scientists all over the world are working hard to create the first functional quantum computer. This is a very challenging task that may take several more years or even a decade to accomplish. The timeline for its development depends on factors like technological advancements, new discoveries, and the availability of resources. To build quantum computers, scientists are combining knowledge from different fields like physics, computer science, and engineering. They use different techniques, but two main approaches stand out: gate-based quantum computing and adiabatic quantum computing. In gate-based quantum computing, scientists manipulate and control individual quantum bits, called qubits, to perform calculations. They are designing new qubits, such as superconducting circuits and trapped ions, to make them more stable and reliable. They are also working on reducing errors and developing ways to fix mistakes that can happen during calculations. Adiabatic quantum computing focuses on creating a quantum system that gradually evolves into a final state, representing the solution to a problem. This approach takes advantage of a quantum phenomenon called quantum annealing to optimize complex problems. Scientists are experimenting with different materials and designing specialized devices to improve the performance and scalability of adiabatic quantum computers. Developing quantum computers is challenging because quantum systems are very sensitive to their surroundings, which can cause errors and disrupt calculations. Scientists need to find ways to maintain the delicate quantum states necessary for computation, known as quantum coherence. Quantum computers also require a highly controlled and isolated environment with extremely low temperatures. Creating and maintaining these conditions is difficult and resource-intensive. The fragility of qubits and the need for ultra-low temperatures present significant engineering challenges when trying to scale up quantum computers. Another important aspect is developing error correction mechanisms. Errors that occur during quantum computations can get worse over time and affect the accuracy of the results. Scientists are researching error correction codes and techniques to address this issue. However, implementing error correction adds to the hardware requirements and complexity, making the development process even more challenging. To overcome these challenges, scientists are collaborating and sharing knowledge and resources. Governments, academic institutions, and private companies are investing a lot of money in quantum research and development. Initiatives like IBM Quantum, Google Quantum AI, and Microsoft Quantum are leading the way by providing access to quantum hardware, software, and educational resources to researchers worldwide. Continuous innovation in quantum algorithms and software is also contributing to the progress of quantum computing. Scientists are exploring various applications like optimization problems, machine learning, cryptography, and drug discovery, where quantum computers have the potential to outperform classical computers. Scientists believe that quantum computers have the potential to transform various fields, including space exploration and the search for extraterrestrial life. One of the key advantages of quantum computers lies in their ability to simulate complex systems more efficiently than classical computers. In the context of space exploration, this capability becomes invaluable. Quantum computers can accurately model the behavior of celestial bodies, such as planets, moons, asteroids, and comets, as well as the dynamics of astrophysical phenomena. By running simulations on quantum computers, scientists can gain valuable insights into the formation and evolution of galaxies, the behavior of black holes, and the birth of stars. These advancements can contribute to refining our understanding of the universe and informing future space missions. Additionally, quantum computing can play a crucial role in optimizing spacecraft trajectories. Traditional approaches to trajectory optimization involve complex calculations and approximations due to the vast number of variables involved. Quantum computers can simplify this process by efficiently solving complex optimization problems. By leveraging quantum algorithms, scientists can fine-tune spacecraft trajectories to minimize fuel consumption, reduce travel time, and enhance mission success rates. This optimization can significantly improve the efficiency and effectiveness of space exploration missions, leading to cost savings and enabling more ambitious endeavors. Space exploration generates a tremendous amount of data that scientists must analyze to extract meaningful insights. Quantum computers possess the potential to accelerate data analysis tasks, enabling researchers to process and analyze large datasets much faster than classical computers. By harnessing the power of quantum algorithms, scientists can efficiently mine astronomical data, identify patterns, and detect anomalies that may signify the presence of extraterrestrial life or provide deeper insights into cosmic phenomena. The enhanced speed and capacity of quantum computers can unlock new discoveries and push the boundaries of our knowledge about the universe. Another area where quantum computers can make a significant impact is encryption and communication. Secure communication and encryption are critical in space exploration missions. Quantum computers offer an advantage through quantum cryptography, which leverages the principles of quantum mechanics to ensure secure communication channels. Quantum algorithms enable the generation and distribution of unbreakable encryption keys, making communication between spacecraft, satellites, and ground stations more secure and resistant to hacking attempts. This advancement in encryption technology is vital for protecting sensitive information, maintaining data integrity, and ensuring the success of future space missions. The search for extraterrestrial life has always fascinated humanity. Quantum computers can play a transformative role in this quest by enhancing our abilities to analyze and process data related to the search for alien life. By analyzing vast amounts of data simultaneously, quantum computers can assist in analyzing radio signals, identifying potential patterns or signals from extraterrestrial intelligence, and distinguishing them from background noise. Processing these signals more efficiently and effectively can improve the chances of detecting and communicating with alien civilizations if they exist. Quantum computers have the potential to revolutionize several other fields beyond space exploration and AI. Scientists believe quantum computers can bring transformative advancements to areas such as drug discovery, material science, optimization, finance, climate modeling, and more. The process of drug discovery and development is time-consuming and costly. Quantum computers can help expedite this process by accurately simulating the behavior of molecules and their interactions. With the aid of quantum algorithms, scientists can model chemical reactions and predict the efficacy and safety of potential drug candidates more efficiently than classical computers. This enhanced simulation capability can lead to the discovery of new drugs, the optimization of drug formulations, and the identification of personalized treatment options. Material science and engineering can also benefit greatly from quantum computers. By enabling more accurate modeling of material properties and behavior, quantum computers can aid in designing new materials with tailored properties. His capability is invaluable for industries seeking advanced materials with enhanced characteristics like improved conductivity, increased strength, and superior thermal properties. Quantum computers can drive innovations in electronics, energy, aerospace, healthcare, and more. Optimization problems are prevalent in various sectors, including transportation, logistics, finance, and manufacturing. Quantum computers excel in solving complex optimization problems by exploring multiple possibilities simultaneously. In transportation and logistics, quantum algorithms can optimize routes, schedules, and distribution strategies, leading to more efficient and cost-effective operations. Similarly, in finance, quantum computers can improve portfolio optimization, risk assessment, and pricing derivatives, enabling better investment strategies, risk management, and economic forecasting. Climate modeling and environmental studies can greatly benefit from the enhanced capabilities of quantum computers. By simulating complex climate systems and interactions, quantum computers can provide scientists with a deeper understanding of climate dynamics. This can lead to more accurate weather forecasts, climate projections, and environmental risk assessments, aiding in the development of effective strategies for mitigating and adapting to climate change. Quantum computers can also play a role in the field of cybersecurity. As quantum computers advance, they have the potential to break existing encryption algorithms. However, they can also provide solutions through quantum cryptography, which leverages the principles of quantum mechanics to ensure secure communication channels. Quantum algorithms can generate and distribute unbreakable encryption keys, making communication more secure and resistant to hacking attempts. This advancement in encryption technology is crucial for protecting sensitive information and ensuring secure communication in various sectors. Additionally, quantum computers have the potential to enhance complex optimization problems in the energy sector. By optimizing energy distribution, resource allocation, and grid management, quantum algorithms can help improve energy efficiency and promote the integration of renewable energy sources into existing power grids. Scientists and researchers are really excited about quantum computers. They think these computers have a lot of potential, but they are also a bit worried. They are concerned about how this new technology could affect security. You see, quantum computers are really good at breaking encryption methods. Encryption is a way to keep information safe and private. It's used for things like online transactions and protecting important data. Quantum computers is really hard. Quantum systems are very sensitive to noise and disturbances. It's difficult to keep the delicate quantum states stable. Scientists need to find ways to correct errors and make the quantum bits more stable. It's a complicated task, and it makes us wonder if we can even build big and practical quantum computers. Another thing to consider is that quantum computers are not better than regular computers at everything. They are only good at certain tasks. Regular computers are still better for most everyday tasks. Scientists say we should focus on using quantum computers where they can be really helpful. This way, we can use our resources wisely and make the most out of both regular and quantum computers. Finding good algorithms for quantum computers is also a challenge. Algorithms are like instructions that tell the computer what to do. Scientists are working hard to come up with algorithms that take advantage of the special properties of quantum computers. But it's not easy. They need to find the right algorithms for different tasks, and that takes time and research. We need to think about ethics, too. As technology advances, we have to be careful about how we use it. Scientists are aware of the ethical concerns that come with quantum computers. They want to make sure that we use this technology responsibly and that it doesn't get misused. They are having discussions and creating guidelines to make sure that quantum computers are developed and used in a way that respects our values and keeps us safe.